Our last section of 5.4 is theorems that work with our definite integrals. So what we're going to do is work through a couple of different examples of how we can apply these theorems. And we will use our graphing calculators for some of them towards the end. So make sure you've got that handy. All right. So we're first going to start with a couple of different properties that we have when we are integrating. Let's look at property number 1. You'll notice here, this is saying if I have a definite integral from a to b of f, if I were to switch my limits of integration, I could do the same, or if I were to switch the limits of integration and negate the integral, those two would be equivalent statements. Let's just, let's see it in play so that it makes a little sense. So we know that the integral from a to b of f of x is the same as big F of b minus big F of a. And you'll see up here I defined what that little f is in relation to big F. Remember, big F is the antiderivative. Well, in that same context, what would the definite integral from b to a of f of x be if I were to negate it? Like this, if we were using our fundamental theorem of calculus. Well, that then simplifies to this if we were to distribute the negative, and then we could rewrite it. And by doing that, we see that those two statements are in fact equivalent. Going through these proofs, let's look at the second example. So that one's telling us that our integral from a to b of f can be broken up into parts. Now, the one thing I want you to be mindful of is I have two different diagrams here. It doesn't matter what our c value is, they're all going to be true statements. The first one, if we see that c falls in between our limits of integration of a and b, it makes sense. Because remember, our definite integral represents the area under the curve, between the curve and the x-axis. So if I were looking at the definite integral from a to b, well, that would be that shaded region. If I broke it into parts and I wanted to represent the integral from a to c, well, that would be this area. And then if I added to it the integral from c to b, well, that would be the area under the curve in between c and d, which we clearly see is the same as that area under the curve from a to b. We're just adding up the parts. What happens if our c is outside of the interval from a to b? Well, it's still going to work. So here I've written that statement out, and what I want to focus on is that part right there. Because if I'm seeing that that's the integral from c to b, and I'm looking at where c and b are, what I can do is I can change those limits of integration so that my b becomes my lower limit and my c becomes my upper limit. But what happens when I change my limits of integration? I have to negate the integral. So now let's look and see what that reads. Now it's telling us that that definite integral from a to b, which would be this blue shaded region, is equal to the integral from a to c, which is that entire region, minus the definite integral from b to c, minus the area of the shaded region from b to c, which clearly shows us that those two statements are in fact equal when we take away that area under the curve from b to c. So why don't you take a look at what these definite integrals are saying, pause and see if you get the same values that I do. So here are the values for numbers 1 through 6, and I'm going to walk through them fairly quickly. Looking at 1, it's that definite integral for, these are all for g, definite integral for g from -5 to 1. That's the area under the curve, and it's clearly marked that it's 4. It's above the x-axis, so I know this is 4. Now, if I see question 2, it's going from 1 to -5. I always want my lower limit to be the smaller value, so what we can do instead is switch our limits of integration and negate the definite integral. So here I know that that would be the same as this statement. which we already found in the first problem. So we know that question 2 is -4. 3 tells us to go from -5 to 6 for this definite integral. That means we're adding 4, and since the area below the areas below the x-axis for the integral from 1 to 6, we're going to subtract. 4 take away 6, 4 take away 10, leaves us with -6. Put it in the wrong spot. Great. Then we're on 4. That's the integral from 8 to 1. I'm going to switch those limits of integration and negate the integral. That gives me the integral from 1 to 8, but we're negating. And I take those areas, and I take -10 plus 7, but then I negate that result, and I get 3. Now let's look at 5. That's from -5 to 8. Looks like we're adding everything that is above area-wise, subtracting everything that's below the x-axis. And with 5, that will give us 4. Take away 10 plus 7, 1. Now 6, be mindful of the order of these operations. For 6, this would be the same integral as this. So the first thing I'm going to do is evaluate that definite integral from -5 to 6 of the absolute value of g. Then I'm negating. And we have -14. Now you'll see on the screen the properties that we have for definite integrals, meaning that if we have the sum or difference of two separate functions, we can either separate them or consolidate them. So you'll see in green, and I'll have you pause and just read this if it's not straightforward. But you'll see in green, there's an example where if my limits of integration are the same, they're going from 1 to 4, I can combine those two functions. And you'll notice that I can work the other way around as well. If it's presented in this form, I can also separate them if that's easier for me to do. And we'll do an example, and you'll see once we start working with these when it makes sense to either separate or condense them. And if I have a scalar, so some constant that's being multiplied, I can pull that out of my integral, take that antiderivative, and then multiply that result by that constant c. And in green here, you'll see the example that follows. I can take the 7 and I can pull it out if that makes things easier. Let's look at this example. It sort of clumps a lot of different concepts together, which I like. So here we go. We're given in this question that the average value of f over this interval from 1 to 7 is 4. And we're asked to find the definite integral from 1 to 7 of 1/3 f of x plus 2. There is a lot to process in this. So let's start with the first piece. The average value of f over that interval from 1 to 7 is 4. That tells me that this has to be true. Then I can just simplify that, and I have this. And now, since I know that that average value is 4, I'm just going to clean that up, multiply both sides by 6. So people, I know that my integral from 1 to 7 of f of x is equal to 24. Now, this is what they're asking me to find. The definite integral from 1 to 7 of 1/3 of f of x plus 2. So the first thing I'm going to do is separate those two. And I get this. Next, I'm going to factor out that 1/3. That's my scalar. That takes me here. Now, I'm now going to focus on that second integral. And I'm going to think geometrically about this. That's the definite integral from 1 to 7 of the function 2. Let's think about what that looks like on a graph. So we're pretty much looking for the area under the curve from 1 to 7 of 2. What would the area under the curve from 1 to 7 of 2 be? Well, that's a rectangle. And I know this base is 6 and the height is 2. So that area is 12. You could also plug it into your calculator, but let's not. So that's 12. Now let's look at the first integral. It's a third of that definite integral from 1 to 7 of f of x. We found from our average value information that that definite integral is 24. So we have now, math, a third of 24 plus 12. And we get 20. Moving on to our symmetry. We worked a lot with even and odd functions, I think, in the previous year. We know that even functions are symmetric over the y-axis. Odd functions are symmetric over the origin. So if I'm thinking about what if I'm thinking about what the definite integral from negative a to a is, I'm hoping that you know that for whatever area this is, because of the symmetry, I know that the area on the other side of the y-axis is always going to be the same. So I should be able to deduce from that the integral from negative a to a of an even function will always be twice the definite integral from 0 to a. Now let's think about what happens when your function is odd. Now, these are still, because of symmetry, equal areas, except one is below the x-axis and the other one is always above the x-axis because of that symmetry. So those two will always cancel each other out and we'll get 0. So let's look at question 10. 10 is asking if our function is even, and we know this to be true. This is 16. What would the integral from 0 to 3 be? So let's try and work this out. We'll first start by separating, and we get this. Now, like the previous problem, I can look at that second integral, and I know that that's asking me what the definite integral is from negative 3 to 3 of the function 5. So we know that area is going to be the area under this curve. So the height is 5. My width here is 6. So this area is 30. And now I have this information. So I can add 30 over to the other side, and I get that that's 46. And because I know my function is even and I want to find the integral from 0 to 3, that's going to be twice the definite integral from 0 to 3 of f of x, which then leaves me with 23. Now let's look at question 11. This is asking us now if our function is odd, and we know this to be true. What would the integral be from 5 to 7? So maybe we'll use that previous property that allows us to separate those integrals. And instead of saying from a to c, I can say that's the same as the integral from a to b plus the integral from b to c. So it looks like this. Why would I think to do that? Well, it's because we know information about the symmetry of even and odd functions. I know that the integral from negative 5 to 5 of an odd function is a big fat 0. So now I have my answer, that the integral from 5 to 7 has to equal 36. Now we've come to the calculator portion of this section, and that is finding the area between two curves. And we're going to use the information that we already know. We know that if we're looking for example, if we're looking for the definite integral from a to b of, let's just say, f, and let's say that blue equation is f, well, if this were my a to b interval, it would be everything below the blue line. And that would be, folks, the definite integral from a to b of f of x. But what if that red line signified g? And I'm taking that away from yellow. Well, the integral from a to b of g would just be what I have highlighted in pink. So if I took that away, we would be left with the area between those two curves. So we're talking about finding the area that is encompassed between two graphs, a function f and a function g. And we always go by the top graph minus the bottom graph. The placement of where they are on the XY plane doesn't matter. It's just which one's above and which one is below. So the area between two graphs, F and G, is always going to be top minus bottom. So here we go. Starting with this first one, we want the area of the region between the graphs x squared plus 2 and y equals negative x from 0 to 1. You're going to take your calculators and you are going to graph both of those. So if we were to graph this, it would look like so. And we want to find that area between these two graphs from the interval from 0 to 1. So we're talking about this region right here. So when I look at that, I'm going to take the definite interval from 0 to 1 of top minus bottom. That's parabola minus line. And our parabola is x squared plus 2, and our line is the graph negative x. And then on our graphing calculators, we're going to go to Math 9, and this is exactly what we're going to type in. Definite integral from 0 to 1 of x squared plus 2 plus x. And the calculator is telling us this, and if we put that into fraction form, if we go to math and then fraction, that tells us our answer is 17 over 6. Let's look at a different scenario. This was an example where the two did not intersect, but we still found the area in between the two from an interval from 0 to 1. So let's look at the next question. We're looking for the area of the region bound by the graph 2 minus x squared and x. You'll notice in an example like this one, they didn't give us the interval in which we were to find that area, but we know that this is the shaded region that we're looking for. So on our graphing calculators, we would then need to find out where those two graphs intersect. And I believe we've done this before when we go to second calc and we hit intersect and it asks for the first curve and the second curve. You'll stop me if that part is unsure. Well, you won't stop me here, but you know what I mean. So we're going to have to find those two x values where they do intersect. And if I evaluate that, and this one's straight because this is Desmos, this gives me that one of those x values is -2, and the second one is at 1. So I know that my interval, or my integral, is going to look like this. The definite integral from -2 to 1 of, and then top graph minus bottom graph. The top graph is clearly the quadratic, the parabola. Minus, and the bottom one is x. And if we typed that in to our graphing calculator, we get 4.5. Now here's the last type of problem, and that's where the two tend to shift places. Meaning, if I were looking for the area of the region that was bound by this cubic and this quadratic, we see, if we were to graph this, that the cubic, which is in red, looks like that, and the quadratic, which is in blue, looks like so. Our area is in two parts. It's in the yellow region and the pink region. Let's look at yellow. Yellow looks like it is cubic on top, quadratic on the bottom. But if you look at pink, pink is quadratic on top, cubic on the bottom. People, when you have multiple regions, the fastest way to do this is by using the absolute value. But in the event that you get a question and it's a multiple choice, I'm going to break it down for you this way first and then show you the absolute value the next way. So multiple choice gives me this. I would start with my integral from, and I would look at my limits of integration. This definitely looks like it's at x equals -2, and that's at the origin. So this is what my yellow region would look like. And for those of you that are doing this on your calculators, I'll show you. I have the cubic in y1. I have the quadratic in y2. Whoops. And so it's a lot easier just to type in y2 minus y1. So we know that that first area gives us 12. Now let's look at the pink area. So this pink area looks like it's going to go from limits of integration from 0 to 2. And in this case, we already identified quadratic minus cubic. So when we write it out, it would look like this. Once again, typing this in to the calculator, we would say 0 to 2 of then y2 quadratic minus cubic, y1. Well, there's also a way that we could do this all in one step, and that's by going to Math 9 and doing the limits of integration from the start of the first point of intersection to the last point of intersection. So that was -2 to 2. And then, folks, we're going to use the absolute value. And we can find that if we go to alpha window. If we go to alpha window, it's also under math, but it takes a lot of time to get there. So alpha window, and there's my shortcut. And I select absolute value. And you'll see automatically absolute value comes in. Now this is useful just because I can do either y2 minus y1 or y1 minus y2. And if I do that all at once, I get 24 instead of having to do the two separately and getting 12 and 12.